Hi, I'm Shihan Seop. Today I'll present homework 3, Spectral Fringe Signal Processing and B-scan Reconstruction, covering lecture 1 through 9. The table of contents is as follows. Let's start with the problem. In this problem, a spectral interferometer records a fringe signal for each of 256 lateral positions. Each row of data matrix is sum of cosines, where each cosine corresponds to one reflected layer at depth g. The key challenge is that the spectrometer samples uniformly in wavelength lambda, but FFT requires uniform spacing in wave number k. Since k equals 2 pi over lambda, is nonlinear in lambda, so we must resample before taking the FFT. The data contains 3 curved tissue layers and 4 intentional artifacts, k nonlinearity, DC backgrounds, fixed pattern noise at depth 65 and 100. Here's the full processing pipeline. We start from fringe raw, apply K resample in step B, then 1D filtering in step C. Step D, reconstruct the B scan via FFT. Step E removes the fixed pattern noise using a 2D notch filter. Finally, step F suppresses speckle noise. Each step outputs a new data matrix ending with B-scan filtered. Task 8. First, we visualize two fringe rows. Row 1 shows stable oscillation, while row 110 has denser modulation due to a Drusen displacing layer 2 over. Second, we demonstrate aliasing. As At 400 Hz, the signal is correctly sampled, but at 200 and 120 Hz, it aliases. The third, we reconstruct a fringe signal using DFS. M equals 250 harmonics is needed to closely match the original. Here are the results. The top plot shows the fringe from row 1. The middle plot confirms aliasing at FS 200 Hz. The sampled points no longer follow the continuous reference. The bottom plot shows DFS reconstruction, improving from M100 to M250, where the signal is well recovered. Task B. Task B addresses the K nonlinearity. Because K is nonlinear in lambda, a direct FFT gives broadband peaks that don't align with the true layer position. We use inter1 to resample each fringe row from K non-uniform to K uniform. Then take the FFT. All 256 rows are resampled and stored as fringe resampled. The comparison is as clear. Without resampling, shown in red, the peaks are broad and shifted, and align exactly with the ground truth layer position marked by dashed line. Task C. Task C applies 2-1D filter. First, a fourth-order Butterworth high-pass filter removes the DC backgrounds below depth 30 Hz. Second, a fire bandpass filter designed using the inverse DTFT method with a Hamming window passes only depth 30 to 220. Importantly, the FPN at depth 65 and 100 lies inside the passband, so it survives both filters. This motivates the 2D notch filter in task E. The spectra show DC removal after high-pass filter. The FPN peaks, marked in red and pink, remain visible even after BPF. The pole 0 plus confirms stability. High-pass filter poles are inside the unit circle, and FIR poles are at the origin. Task D. Task D, reconstruct the B-scan. We apply FFT to each row of fringe filtered, take the one-sided magnitude, and store it as A-scan map, size 512 by 256. Displaying in dB scale reveals both the layer structure and the remaining artifacts. Both the 2D effect shows FPN energy concentrated at lateral frequency Fs equals 0 because FPN is identical across 256 columns. The A scan in dB scale shows the three clear peaks at the ground truth layer positions. The B scan shows the curved layer with the FPN horizontal line and bright spots still visible. And the 2D FFT confirms FPN energy on the vertical axis. This is exactly where we will apply the notch filter. Task E. Task E removes the FPN using a 2D Gaussian notch filter. The same principle as the more removal in lecture 8. Since FPN is constant in the lateral direction, its 2D Fourier energy sits only at fx equals 0. We build a Gaussian notch at depth index 65 and 100 with radius d0 equals 12 and their conjugate positions, multiplying in the frequency domain, then applying IFFT removes the FPN. Before and after comparison, on the left, the horizontal line at depth 65 and 100 are clearly visible. On the right, they are gone. The tissue layers and bright spots remain unaffected. Task F. Task F compares two spatial filters for speckle suppression. Speckle is modeled as multiplicable noise. The Gaussian filter reduces noise but blurs layer boundaries. The median filter removes speckle while preserving sharp edges, making it better choice for OCT B scan. The three images confirm this. The Gaussian filtered result on the middle is visibly smoother, but the layer boundaries are softer. The median filter result on the right suppresses the speckle while keeping the layer edges sharp and well defined. That concludes the presentation. The full method code is available at the solution, and I will going to demo the code. First, A. Oh, wait. First, task A. This is the fringe signal, and this is the A scan of row 1, and this is the A scan of 110. And this is the sampling and aliasing. We can, and next, the DF has fringe reconstruction. This is the original fringe, and we can see over than 250, we can reconstruction well. Next, task B. This is the raw fringe in lambda space, and this is the FFT without K resampling. And we can see the peaks are broadened, but with K resampling, sharp peaks at the correct depths. And C, task C, we can see the after K resampling, and we can use the high pass filter, so the low frequency components are gone. And using BPF, so we can get rid of the high frequency component. That's their noise. And this is the jet pole zero diagrams of both filters. Next, task D. This is the A scan of linear scale, and this is the A scan of dB scale. So the B scan of dB scale looks like this. You can see the FPN line of 65 and 100. And this is the 2D FFT of B scan. And this is the the B scan of still we can see the FPN line at depth 65 and 100. And this is the lateral, these columns. So we can use the 2D notch filter. So we can still there is a FPN lines left, but we can reduce the factor FPN so the tissue are well observable. Lastly, the task F, we can see the speckle corrected B scan and the Gaussian filter and median filter. There we can see the line well in Gaussian filter, but the boundary of tissue are less available. So, but in median filter, we can still reduce the speckle and we can see the tissue very well still. This is my presentation. Thank you for listening.